we'll do a shell balance to derive equations of continuity and motion. An equation of continuity is really a code name for mass balance, or the fact that the mass is conserved. Now, before we do that, what I want to point out in these copies, these are basically individual appendices pulled out and put together just as a quick reference. If you want that reference, feel free to use them up and carry them with your notes rather than carrying the entire book. But what I would like to point out is the following. Let's look at the table A71. Table A71. This is various differential operations in Cartesian coordinate systems. So if you, for instance, look at the first one, that's our divergence, our friend divergence, and how we compute that for a vector field, right? In a Cartesian coordinate system. So if I have a velocity vector v as dvx dx plus dvy dy plus dvz dt. Okay. Now, there are some other ones, and then there is def is the gradient, and you would expect a gradient of a scalar function s look like. So pressure, for instance, is a scalar. Gradient of pressure is dp dx, dp dy, dp dz. Now let's move to the cylindrical coordinate system, which is table A72. What surprises you for divergence, if anything?
It's short.
Hmm?
It's short.
Well, length is irrelevant, but it's not the same as Cartesian. Okay? Compare divergence in Cartesian coordinate systems versus divergence in R theta z. Okay? It's not dvr dr plus dv theta d theta plus dvz dt. Something else. Now you will see our friend 1 over r dvr of rvr. And when we had a form like that with our tensor PRZ, I believe it was, okay, we said that's because of the curved coordinate system and the fact that not at all points you don't have the same sort of, like if you have a little coordinate box, the areas are not the same on all sides. And that's what it's making up for, this 1 over r. And multiplying VR times r. Because at the larger r, the area is larger. So, I don't want you to know this. I will not call you up at 2 a.m. and ask what is divergence in a cylindrical coordinate system. That's technically counterproductive. Okay? But I want you to remember, if in a different coordinate system, look it up. Go to the table, look it up. You will have these tables. You can carry this piece of paper if you'd like, but you will have these tables in your the book will be with you on the test. Just remember to look it up. Don't just go mechanically and say, oh, it must be dvr dr plus dv theta d theta plus. Okay? So in a curved coordinate system, you're going to have that happen. Same thing for gradient. Okay? Look at gradient. def. Gradient in cylindrical coordinate system is not a simple equivalent of Cartesian coordinate system. Okay? So instead of the theta coordinate, it has 1 over r, d, s is for scalar field, d theta. Okay? It's not just d theta. So just have that in mind and look it up. Now, what is here, I'm going to walk through. There's also cylindrical coordinates. After I put these, there's also, we're not going to do much in spherical coordinates, but there's the equivalents for spherical coordinates. And then cylindrical coordinates, there is also definition of cylindrical coordinates. Okay? What is x, y, z in terms of r, theta, and z? So note that you can from here actually see if this is coordinate x as a function of r and theta, you can actually see what is dx, d theta, dx, dr. Right? So x depends on r and theta, and I could take, it's a function of r and theta, and I could take the derivative and relate it. So basically the expressions A6 10 through 12 and A6 13 through 15 allow you to go between r, theta, and z coordinates and x, y, z coordinates. So a general r, this is a coordinate vector delta r expressed in terms of coordinate vectors x, y, and z at every point. And same for theta and z directions. And then the other way around. What I like, so where have you covered different coordinate systems and how to go back and forth between two coordinate representations? Did you do that in some formal linear algebra somewhere? Yeah. So what this is, you can think about this as a vector in r theta coordinate system. That is, so a matrix, cosine theta, sine theta 0, minus sine theta, cosine theta 0, 0, 0, 1, multiplied by the vector, the same vector in x, y, z. Do you all see that? This is a matrix vector multiplication, this one. And the other way, the same, and actually these two matrices are inverse of each other. Did you cover that somewhere? I hope so. Raise it up. So this is just that allows you to go back. Okay. So, second part is then the spherical coordinates, which we're going to look, and we're going to use, so same thing, we're going to use this in solving equations, so I'm just going to now point it out now that I'm talking about the appendices. Newton's law of viscosity, you have expressions, if you keep going from the next page, you have expressions in appendix B1, for all of the tensor, shear stress tensor components in XYZ coordinate system, and you've got the logic already of the appendices, and right after that there is cylindrical coordinate system. So it so happens, if I took a look at tau ZR, it so happens that it actually kind of looks equivalent to our friend tau Ix. It's minus mu dvz, dvr dz plus dvz dr. But that's not necessarily so that they're all equivalent. So just look at it. When solving, take a look. In your appendix, you have your book. Unless you have really good memory and want to memorize. Memorizing a certain amount of information is good because it gives you speed. But there's a whole lot of formulas in this course, so it's a little dangerous to rely on memory. You need to balance that based on your own memory and how well you memorize. Right? So I don't want you to focus on memorization, just know where to look it up. But certain, and if you want to, I will also allow you at the exam to have 2 pages of your own notes. So for instance, oh yes, everything is in the textbook, but it's not quick for you to look it up, and you want to create your own set of formulas that are quick reference, by all means do so. Okay? So I'm not gonna, whatever you want to do on those 2 pages, as long as you don't have a complete solved problem, I'm okay with that. Okay? So essentially just whatever, figure out what works for you, but it is true that this is, the solving problems is difficult in this course, and it's a lengthy procedure. So you have to figure out how are you going to figure out your way of attacking the problem. And that kind of depends on each and every one of you will have a slightly different approach. Okay? All right. Okay, so now we will move on to doing a mass balance, because we haven't really done that. We had it actually built in certain assumptions, and we're going to show how that was the case. So I'm titling, oh, what am I titling? HDMI.
There we go. The title is Isothermal Equations of Continuity and Motion. Again, equation of continuity is a code name for mass balance. Equation of motion is essentially momentum balance. Or, as the case might be, imbalance, but we will have an equation that accounts for it. Okay? So for reading, chapters 3.1 and 3.2 are relevant. We will skip equations of energy and angular momentum for now, and then 3.5, 6, and 7. Okay. So what is equation of continuity? The basic idea is, and I'm going to stick to the coordinate system in proving main points, because choice of a coordinate system is arbitrary. And we would do a similar approach in a cylindrical coordinate system, but we would get ever so slightly different result in terms of the equation, but you will just be able to look that up. So, okay. The basic idea is that if I have a box like this, okay, I want to account for the change of mass in that box. And I have a fluid flowing. I know that I have a velocity field in a fluid of density rho moving through this box. So how do I account for mass? So velocity gives me the momentary motion of the fluid, right? So if I'm gonna basically just tally up what's basically arriving into this box, I can look at the flow through the boundaries of this box. Okay? So I can enter into this room only through that open door, and I can enter into the room only if I'm going orthogonally through. Okay? If I go tangentially, I ain't gonna go in. Okay? So the way we account for that is by projecting things onto the normal on that surface. So there is a normal direction to my door, right, or any side of this wall, and I can enter through only normally too. So basically, I will look at what is coming on through this side here. So this is my what we call lower x side. So this is going from x to x plus delta x, in y direction y to y plus delta y, and in z direction z plus delta z, right? That's our standard little box. So what is going on if I have fluid of density rho moving through with velocity v? How much of fluid is coming through this box? I can think about that velocity v carrying a little bit of mass, but I'm going to have to express that in terms of density, right? So rho v projected on the side in the normal direction, yes? It's moving with velocity v, right? So basically rho v dot this delta x. And when I look at the v dot a coordinate vector x, well, that's my x coordinate by definition, right? Any vector times the coordinate vector x is an x coordinate. If I dotted it with the delta r, the r coordinate vector, it would be r coordinate, right, of the vector v. So this is rho vx, and I'm going to evaluate that at this side x. Okay, that's what's momentarily coming in. On the other side, if I'm thinking of things coming in, well, to come in, I would have to have direction that is minus delta x. Otherwise, I'm not coming into the box. Do we agree? I'm leaving it. Okay. So basically, on the other side, I'm going to have the same projection, but on minus delta x. Right? So it's going to be minus rho vx, but evaluated at x plus delta x. Are we okay with that? So when now this is all per area, right? So I have to multiply by area in order to come in. So basically what we are going to have is rho Vx at x times the area, which is delta y and delta z. Okay? And then that minus rho Vx at x plus delta x times delta y delta z, also area. So that's accounting for things coming in this way and this way, right? And I do the same for y direction and z direction. That's this. Rho Vy evaluated at y times area is now delta x delta z. That's this front here. Yes? Minus rho Vy at y plus delta y times delta x delta z. And plus rho V eval. So now that I have the bottom here, rho V z times area delta x delta y. And on the other side, this is what we call going out, right, of the box. That's why we are subtracting in minus out. And formally we think of it going out because basically velocity is probably on that little of a box all in the same direction. So on one side it's coming in, on the other side it's coming out because it's the same velocity is oriented opposite of the normal on this side, of the normal coming into the box, right? So that's what we physically say in minus out. Okay, so this is now accounting for all of the stuff that is coming into the box, or maybe it's coming out depending how velocity is oriented, but we are thinking about it as coming in because we are working with the directions of this coordinate system. That's basically what is the momentary change of mass, rho times volume. Yes, so this is mass. Density times volume, dm dt is equal to what's coming through the side. There's no way to change mass if I don't have a reaction inside. And we are not assuming any reactions right now inside. It's just a fluid. It's a continuous phase. Nothing's changing. Then the only way to change mass into that box is to go in through the sides or possibly leave through the sides. Either way, I gotta go orthogonally to the sides to actually change anything. Yes? Should I repeat this process? So this is basically shell balance. I'm just doing this in time part as well. I could have just said that all of this is happening in delta t, so I could have multiplied the entire side with delta t, and then delta of mass is some finite amount of time. Delta t times velocity will give me the distance the fluid moves in through an area, and that's essentially the volume change within, yeah? Times rho. Once again, so we have a box, we place a box. The basic idea is that what's going to change volume in this box has to come in orthogonally through the boundaries. And I have 6 boundaries to look at, 6 planes. Okay? My velocity already looks in time. It's a momentary change in distance. So there's a velocity coming through here. And what comes in, it's carrying certain element of density rho. So that's what's coming in through this side per area, right? So to collect how much it's coming in, I gotta multiply with area. So then rho v times delta x is basically projection of what comes through this side, evaluated at x. On the other side, in order to come in, I have to project on something that is oriented in negative delta x direction. So I do that, so it's minus rho vx evaluated at x plus delta x. So when I sum those two up, I also have to multiply by area, because this is all per area, to get the volumetric flux in, yes? This was just a linear flux in. To get the volumetric flux, it's basically V times area, right? Excellent. So when I do that, this is essentially what's coming through in x direction. And then for y and z direction, I have pretty much equivalent way of looking at it. So I gotta sum up all those. So I have 6 sides of the box altogether. When I put that all together, that is my momentary change of mass, rho times volume, in this box. Questions? This is the first. Is this your first or second class this morning? First one, and so for some of you second. I have already put you to sleep. Oh my goodness. All right, but this is a shell balance. Does everybody essentially recognize the shell balance? It's just that now I have the time component. The way we were solving the problems with shell balance, we were saying, well, the change is 0 because it's a steady state. There's no change in or accumulation in time. And now I'm possibly accumulating in time. Yes?
So in the shell balance, we like had it going in and going out. Can you explain again why it has to be a negative delta? Or?
Because in order to actually, what's going to change inside of the volume, I kind of come in opposite directions. Because the directions of the normals for these two sides are opposite each other.
Okay.
Right? In order to actually accumulate in this volume, or not accumulate for that matter, right? This change in time could be 0, right? So I have to basically balance things, but if I'm looking at the net inside, on this side I'm coming in this way, on the other side I gotta come in oriented opposite of the coordinate system. And that's what we count as out. But technically I'm collecting what's coming in through all of the boundaries, however they're oriented. But if I'm in a coordinate system and I'm placing these boxes in coordinate system, and they might be curved, one of them will be in the direction, and the other one that I hit, in order to come in, I have to come in the opposite direction of the coordinate system. However, I put 2 parallel boxes, and I'm looking of something in between them. Yeah? And that's what we refer to as out. On all of these boundaries, depending if this velocity is oriented in this direction, I'm going this way, counter x, right? Then I'm coming in here and out here, technically. And that's going to be accounted for with a different sign here. So whether this is positive or negative, like if overall this change could be 0, positive or negative, right? So overall net, I might be leaving the volume or accumulating on the volume or having a deficit or not having a deficit at all. But that's gonna be these signs that are gonna work themselves out. We just formally think about it as in and out, right? Because and this minus comes in from the fact that this normal is negative orientation to this one. That's all. Yes? Really, what I'm really doing is I'm summing things over the boundaries, all of the boundaries, however it is that they're oriented. And these are my normals to the boundaries. And if I have a coordinate box, then my normals to the boundaries are simple, and projections on them are my coordinate values, like Vx, right? That's my x-coordinate for vector B. So it's easy to then look at things, right? Because that's how we are envisioning vectors, that's how we are visualizing vectors anyway. Yeah. So technically, if you have done surface integrals, okay, this is technically a surface integral of rho v over the boundary of this box. Okay. And to do a surface integral of a vector field, I gotta project the vector field on a normal to the surface element. So then integrate f dot n dA. Do you remember that? No. Okay, then just forget about it right now. we might need to have a calculus review with a transport angle or fluid mechanics angle, because I think that's where you actually need that calculus for. So I will review my free time, which is kind of short, and we will organize those. Or maybe I just record videos. But if I just record videos, you might see them, you might not see them. It's better if you're in front of me. Okay. So I will consider it. So okay. So now, can everybody write this down? And then divide by volume and send delta x, delta y, delta z to 0, please. So divide by volume, then take a limit when I say shrink the element, take a limit when delta x, delta y, delta z all go to 0. So I shrink the element. That's in essence how you obtain differential equations for anything. Do a balance over an element and then shrink it to a point. So what do you get as a partial differential equation? So on the left-hand side, you have d dt of rho, I hope. This entire equation, when you divide by delta x, delta y, delta z, which is the volume of the element, what's left on the left-hand side is d rho dt. Did everybody get that? That part should be simple. Okay. Now this first set, when I divide by delta x, delta y, delta z, then I have rho vx evaluated at x minus rho vx evaluated at x plus delta x divided by delta x. Yes? When I shrink that, when I take delta limit as delta x goes to 0, what is that? Negative partial derivative with respect to x of rho vx. Yes? Take a moment to see that, find that. If you have trouble seeing it, call me please, and I'll come and take a look. Again, this is one of the standard things we do in shell balances. I want you to have that down. What about the next one? When I divide this, delta x, delta z, which I have in both of them, by volume, I'm going to have rho Vy evaluated at y minus rho Vy evaluated at y plus delta y divided by delta y, right? When I take limit as delta y goes to 0, that's essentially negative, because I started with y instead of y plus delta y. It's a negative derivative with respect to y direction, partial derivative, of rho Vy. Yes? And similarly, the last one is going to be divided by delta z when I divide by volume. So I'm going to have a negative derivative of rho Vz in z direction. Yes? So I have x coordinate of rho v vector, y coordinate of rho v, and z coordinate of rho v. This is divergence of rho v. This is why divergence, if you think about divergence, think about collecting contributions coming into a volume through the surface of whatever. In this case, we're looking at momentum or velocity at a point carrying in mass density with it, right? So my mass conservation in this, accounting for everything, is that the change of density in time is negative. I have to come through the volume, essentially, from the outside coming in against the outside normal, delta dot, so this is my divergence of rho v. Or d rho dt plus divergence of rho v is equal to 0. That is mass balance or equation of continuity. So now what happens? So everybody got this? Okay. So now assume rho is a constant. It's just a number. What is d rho dt? 0. And then I can divide by rho. It's a constant. So I will get the divergence of v is 0. So for fluids of constant density, saying that they're incompressible and mass is conserved is basically equivalent to saying that divergence of velocity field is 0, or velocity field is divergence free. And if you remember, have you all watched that Khan Academy video? So now it's time to look at the divergence video again. And now that you know this, kind of let that sink in once again, please. So basically, those sinks, right, will have non-zero divergence. Those fields that actually have stuff going in. So if I'm producing into my wellbore, right, I have a sink in the wellbore, and I'm constantly taking stuff out of it, right? Divergence around that is non-zero. And since I'm collecting, technically divergence is negative, so then overall I'm having a positive change in mass if stuff is constantly coming in, right? And if I have a positive divergence, right, then I'm losing, then I have a source. Stuff is constantly coming out. So that's happening during injection. Yes? Okay. So we have answered what does equation of continuity look like if density of fluid is constant at all times. Now, there's another consequence that we're not going to work on in class, but if an incompressible Newtonian fluid is flowing next to a solid surface, then components of the viscous stress normal to this surface have to be 0. So that's sort of a consequence of conserving mass. All right, now we're going to do pretty much similar thing. We're just going to look at the volumetric change of momentum. And now that we're not looking at mass anymore or density, which are scalar fields, essentially you have to now move in to vectors, and vectors we have to consider component by component. So my volumetric change of momentum in time within the same volume element is the net momentum flux going through the boundary of the element. However, I have to account for any action of external body forces as well on the momentum, because they can change momentum. Force field can change momentum. If we jump out of the airplane, we can feel how gravitational force field of Earth is changing our momentum big time, right? So now we actually do the same thing, and if I look at the X momentum, and this is essentially what we were doing in the shell balance. It's just that we were assuming for steady state that this change is 0. And right now it's like it's some change in time. So change in time on my rho Vx is my shear stress already has components that are coming through the boundaries, right? And that's essentially what we were doing when we were doing shell balance. So I immediately put that this is negative ddx of phi xx, okay, because that's x momentum coming through x boundary, yes? X momentum coming through y boundary, x momentum coming through z plane or z boundary on a box. So I have really divergence of what we are referring to as phi x, my x momentum vector. And what can also change is the action of the outside forces, and we are referring to rho g as the general expression of a body force. So there's some acceleration related to it that we call g. And gravity is the most common external body force. You could have, for instance, magnetic forces acting as well, and you would just add them up here if you knew how to evaluate them, right? So this is something we already had. If you remember when we were doing thin film, we didn't have this part because we ignored the y direction, right? But we had minus ddx of phi xx and minus ddz of phi zx plus rho gx. Yes? So basically my x momentum balance is d dt of rho vx is equal to divergence, negative divergence of my phi x plus rho gx. And you would do the same for y and z. Okay. So technically I have these three equations. And I'm just going to say something so you have something to hate me for today, entire day. So now we're going to introduce, divergence of a tensor. Simply to express these three equations. It's a vector equation, therefore it has three components. And if you want to express them in a short way, you just write down that this is d dt of rho v, yes? And I'm just going to define a divergence of a tensor as a vector that has each component is a divergence of a coordinate component of that, yes? Now divergence acts on a vector. If I had tensor, basically I'm going to act on the first column of this x column of this vector. That's going to be this. divergence of this column is going to be this, and divergence of this column is going to be this. And then I get 3 coordinate components, and that's what I call divergence of a tensor. This tensor, right? This was my phi x, this was my phi y, this was my phi z, as is. And this is just rho g. So this is a vector equation. And this is cryptic, but it was devised in order to make writing of this shorter. So you write 1 equation, not 3, when you need it. Also, this equation, as expressed here, does not depend on choice of the coordinate system. So technically, this is correct regardless whether I'm in x, y, z, r, theta, z, or something else. Do you hate me yet? Can we deal with the divergence of a tensor? Divergence of a vector is a scalar value, right? I get one number by diverging, if you will, a vector, because I go to coordinate components of that vector. So for instance, dvx dx plus dvy dy plus dvz dz. So I come up with a scalar, right? And that scalar basically, as we saw, expresses how does this field act as a source or sink at a point? What is my sort of balance of mass, if that's okay? Now, my divergence of a tensor is just simply putting together, for a tensor, I look at every matrix as collection of vectors, and I'm going to just go vector by vector and put divergence of the first vector, divergence of a second vector, divergence of the third vector into a vector. And that's going to be my divergence of a tensor. Whew. You have survived for now. Now we'll see whether you remember anything on Friday. Yes, I will go over this on Friday. Okay. So I'm going to stop here and we will continue on Friday. So we have derived our equations of continuity and motion, and then we need to put them in practice.